All right. How did you guys feel about the exam? Rough. Do I have an echo here? Um, I've graded part of it, mostly the first problem so far for most of the exams. Not everybody yet. Um, so that's all I've seen so far. Probably won't have them finished by Thursday, but good chance for next week, Tuesday or Thursday. So felt rough. Was there anything in particular that was trouble, or just kind of the whole thing?
The last two parts, I kind of had to think with that.
So the last final problem, or well, I guess the last two problems of the last, yeah, that was sequencing the plug flow reactors, right? I I intentionally put that towards the end, and I'll probably be pretty lenient on that. It turns out the solution is simple, but it does make you think, right? And if you haven't been thinking in that terms, and we did CSTRs in series, so we'll talk more about that next week when I pass those back. But I get that. Anything else that was surprised you or anything?
I just overthought the first one.
Okay. Yeah.
Especially the last, like I think the last part of the first one.
Yeah. Yeah. So problem one, part like the part D or whatever. I think all you really needed is one piece of information in there, and then the rejection fraction. I think that a lot of people have been overcomplicating that from what I've seen so far. Right. Now, as you know, I do give partial credit. Trying to see how much you learned with it, right? So, but we'll come back to that next week. So, speaking of schedule and stuff, where are we? Let me pull this up for us. Okay, so just a quick little note. Today we're going to go through basically the intro, the fundamentals of wastewater treatment, why we care about it, what are the driving regulations and desires for treating our wastewater. We're going to use a lot of the same types of technologies as we've been talking about. We'll use sedimentation, things like that. So some of the components we've already covered that are relevant to wastewater treatment. And so here, what we're mostly going to focus on is the biological aspects of treatment, making use of microbes in order to do the removal of the waste that we want. So in some aspect, we've covered disinfection, which we often do for our wastewater. We've covered sedimentation, which we use in our wastewater. We'll see in a moment. And so now we're really going to narrow it to primarily these biological aspects and understanding more about that. Okay, so that's kind of just a glance at where we're at. Speaking of disinfection, if you recall, we talked about that fecal-oral route of transmission. We also mentioned typhoid fever and its decline in the States, correlating with chlorination beginning, but it's also a matter of the other side of things, cleaning up our wastewater, right? So as we consider the timeline for typhoid, rates of typhoid fever deaths, there's modern medicine, there's chlorination, and there's also better wastewater control, right? So each of these components are going into there. It'd be hard to say exactly what fraction or percentage of this is one or the other, but these are all going kind of to the same place. So, as we think about wastewater, we might think about local pollution, and here's a few problematic wastewater discharges I've seen. These are from trips I took to Nicaragua in the past. We have on the top an open, unregulated gold mining operation, so they're milling ore in these kind of container things with mercury, and so then certainly there's a bunch of mercury. They're going to try to keep as much as they can, but there's going to be a lot of mercury lost straight to the discharge, and that's just going to be emptied out into the local creek or wherever it happens to land. That's what's happening in this sort of a makeshift stirring, grinding sort of a thing they've got. And the discharge here, it's got something here. It's got a little retention pond kind of a thing, probably to help catch anything that they wanted to keep, but it's not so good. Down here we see a discharge that looks, you know, like super green, gross. It's actually probably mostly algae, but this is running straight through a landfill, and people are kind of digging around for recyclables there. It's pretty unfortunate scenario when that just goes straight into a river. So the deal is that it's green because there was a wastewater treatment of sorts upstream of this, and so they're using some kind of like a lagoon type of treatment. We'll talk a bit about those, and then just discharging it straight through here. So not probably adequate treatment, and the fact that it's running through an active landfill is even worse, because then it's going to catch a whole bunch of other contaminants and send them out to the river. So we've seen this image before. We've talked about our water treatment side. How do we make it drinkable? And now we want to consider, given scenarios, kind of worst case scenarios like that we might find, what do we do to prevent the worst case? What is the worst case? So what is the role of our wastewater treatment before discharging to the environment, right? So most of environmental engineering comes down to either protecting ourselves from the environment or protecting the environment from our activities. Usually a combination of both, right? We want clean drinking water, and we don't want to kill all the fish in the river, right? We want both of those things. And they're not, fortunately, mutually exclusive. All right, so here we have kind of a typical wastewater treatment design or plan that you might find. We'll have a collection system, that's our sewer system. In Baton Rouge, it's kind of interesting because it's so flat, we have to do a lot of pumping. A lot of cases we'll design for gravity lines. So if you ever work in anything relating to wastewater, you might find you have gravity mains and force mains. The force main is you're forcing the water through. It's pressurized in that sense because you're pumping it. Theoretically, if we could, we'd always let gravity do the work for us. And so we would have our sewer plant kind of at the lowest geographical area generally to allow gravity to collect things. Or maybe you'd have a pumping station, a force main, to bring it up to a certain spot and then allow gravity to take it from there. Here we generally have mostly just force mains because that's what we have to do. Okay, so you'll collect your wastewater, then you'll send it through some sort of a screen and grit chamber, something to collect the larger particles, larger stuff. Maybe somebody accidentally flushed a pen down the toilet or something, and where is that going to make it? You know, eventually it'll probably be removed in this spot if it makes it there. Then we're going to use gravity, right? Sediment what we can, do primary sedimentation, take out anything that will settle. We'll do that, and then send that to sludge processing. From there, we get to the biological activity. So the primary sedimentation, we also often call these clarifiers in the context of wastewater. So in drinking water, we usually refer to them as sedimentation basins. In wastewater, we often say clarifier. It doesn't have to be that case, but that's just generally. So from here, if we do some basic physical removal and then basic physical gravity separation, we call that primary treatment. So if we are achieving primary treatment of wastewater, that's what we've done. Basically used the most basic things we can. We're not filtering in like a membrane type sense. We're filtering in like a, hey, we've got, just flow it through this rack of bars to prevent any big objects. That's not gonna require any extra force really. It's just gonna flow right by and catch a few things. It's just gonna be a matter of cleaning up the that grit chamber, the screen, the bar rack, whatever. And then gravity. Okay, from there, we send it into our bioreactor. And so now we're talking about secondary treatment. We're using bacteria, sometimes algae, sometimes maybe there's some fungus or different things, but mostly bacteria growing, and we give them a whole bunch of air. So we're bubbling water through, or bubbling air through the water typically, if we're doing an aerobic process, and basically giving them the perfect environment to grow and eat stuff. Because what they're going to do is they're going to take all the dissolved things. Maybe there's some sugar in the water. Maybe there's some dissolved, like urea, for example, right? There's all sorts of organic materials that could be nutritious for an organism. And what we want them to do is take these dissolved components and transform them into solid components, because we have a much easier time catching a solid than catching an individual molecule, right? When we want to treat our wastewater, it's much more handy, much more convenient if we can transform it from that dissolved sugar molecule into a cell that could attach and clump up together and physically just drop out of solution, right? So it all comes back to the silly little diagram I showed at the very start, right? We have some process, we have some stuff, and we want to get it to just a little pile of stuff, right? We're going to use the bacteria to achieve that. And that way we can physically remove the bacterial cells by the end of this process. Okay, so we go through a bioreactor. Conventionally or typically, we would call this a waste-activated sludge reactor, or this would be a waste-activated sludge process. We're calling it activated because we're activating it with bubbling air through it, or oxygen. Usually it's just air. It's making a sludge of bacteria. So we refer to it a sludge, or sometimes a mixed liquor. We'll call it mixed liquor suspended solids sometimes. And sometimes, in particular scenarios, we might want to do it without the oxygen and use different types of organisms that do anaerobic processes. It gets a little more advanced with the biochemistry stuff, but you can sequence back and forth if you want to get fancy. But in essence, a secondary treatment typically employs an aerated waste system, aerated bioreactor at least. And then we have sedimentation again to catch all those bacteria we just made. Presumably then, most of the bacteria are gone by the time we're sending it out. Now, I say most by mass, but there's still going to be plenty of bacteria that didn't clump up with others and settle out. So there's still a need to disinfect. It's not like the sedimentation can get all the bacteria, but when we're growing them in such huge quantities, they're going to stick together and make a sludge. From there, we'll find that we typically recycle some of that sludge straight back into our reactor to keep the same type of bacteria that are being very useful for us, to keep them growing and happy. Because if we had none of them return, then we'd have to start from scratch every time. So we like to keep a high concentration of these bacteria in there so that they are constantly consuming a bunch of waste. We'll cover more about that in a lecture or two. Likewise, we send some of that to sludge processing. So it turns out that difference, how much we recycle or how much we send to waste there, it will end up being very important for us. So like I said, we'll come back to that. We often have disinfection added there for our discharges, and that would constitute our secondary treatment. Maybe if we were doing some fancy nutrient removal stuff, if we had a phosphorus problem or a nitrogen problem, we might add a tertiary step. And this would typically be introduced actually before the disinfection. So we would kind of put in tertiary and just do disinfection last. Disinfection is kind of going to be last, and we generally just lump it in with secondary treatment. Okay, so that's a typical wastewater operation. So what we're going to do today is talk about, well, what do we have to achieve with this wastewater treatment? What we're going to talk about next time is going to be, all right, how does this bioreactor thing work? And how do we get a handle on the important mass balances that are going to be involved with knowing how much waste can we remove and how does that relate to the bacteria that are there, because those are the things that we can manage. Okay, so wastewater regulations. Oh, and by the way, I'll probably, including, today we'll probably cover this first initial step, the screen bar rack stuff. It's just a couple minutes to chat about what that looks like in practice. So we'll start that today, but that's pretty minor. Okay, so regulations and standards. Well, typically what we're going to do is treat our water in such a way that whatever body of water is going to receive the wastewater is not going to be significantly harmed, right? We want to protect specific aspects of that receiving water. If we're discharging into the Mississippi, well, down here, the Mississippi's got a lot going on in it already, and so our wastewater may not impact it too much. But if you're discharging into a small stream that's very clean and clear, it's got a lot of wildlife in it, that could be a different story, right? And we want to protect that in order to maintain as close as we can kind of the natural state of what's going on there. So the way we enforce that is a program called the National Pollutant Discharge Elimination System, NPDES. I worked briefly for Michigan's NPDES program. So I have some slides. I received a training on that. I'm going to share a little bit about that with you. That was in 2015. There's been a few updates. There generally are, but nothing too major so far. So their goal originally was to reduce and eventually eliminate all discharges of pollutants to surface waters. So that was the initial setup, what this NPDES program was aimed at. Eventually they recognized that, well, elimination of any pollutant is probably not actually practical, especially since you can treat temperature as a pollutant. So if your temperature is different, that would be a problem. It also turns out that sometimes you might have, if you get a really, really clean water, but it has just a little bit of contaminant in it, you might have a situation where you're trying to eliminate that last bit of contaminant, let's say a tiny bit of, ammonia, just a really small amount. And you're discharging to water that has much more ammonia and all sorts of other parameters that we might call contamination if it was in our discharge. So by discharging this really, really clean water to the receiving water, we've changed the water quality in a way that could disrupt the ecosystem for trying so hard to clean it. So at some level, it doesn't make sense to eliminate everything. And if we were to put our energy, that much energy towards it, it would never be cost effective to do many of our industries. Even generation of power, right? We end up using water as part of the Carnot cycle for thermodynamics to receive temperature, to have a temperature differential. So we're taking in a bunch of water, we're using that as a cold source, and we're generating hot water. That differential gives us the energy that we can harness. And then we discharge, typically we send the hot water that we made through some cooling towers and then discharge it. And it's warmer than the natural environment typically. So even that could present a problem where it just would make energy quite costly to produce. Okay, so in essence, what we then aim to do is protect all intended uses for the receiving water. Now, what we might intend for receiving water to function for us as society, as humanity, largely it's things like maybe being an acceptable supply of drinking water, something that we could use as a drinking water supply if we needed. Recreation, whether that's boating, swimming, fishing, something like that. The capacity to maintain natural ecological functions, wildlife, things like that. We don't want to kill off all of a particular species of animal. And if we are discharging to something that there's an endangered species, we intend to protect it, right? One of the intended uses there is people care about the environment. People care about different species and conserving what we have. So there are intended uses, even if you don't care about fishing, maybe somebody else does. Or maybe if you don't care about this endangered species, well, there are people that do. So that's one of the intended uses that we want to protect. Another thing that these regulations do that actually feels counterintuitive, if you stop and think about it, our permitting programs, we'll talk more about it, but the NPDES program in particular acts like a license. Like you get a license to drive a vehicle on the roads, right? That's issued from the government. You are now permitted to drive, okay? That can be revoked if you misbehave and violate the terms of it. Likewise, the EPA or a state agency through the EPA, or the EPA through the state, can authorize people to discharge water, wastewater, if they meet certain requirements. And so thinking about the permit that way this means that the industry producing the wastewater is no longer liable for the damage that wastewater might cause. Assuming they're following the regulation, it's actually the EPA that's at fault for giving the permit. So if they're permitted to discharge, that company now is safeguarded against lawsuits and blame. So it feels like, and if you talked with people in industry or anybody that's connected to regulatory systems, they might complain about, oh no, the regulations are too harsh. Maybe so, but one thing that is often missed there is the other aspect of it are the regulations are going to allow a company to discharge and be protected from the lawsuit. So if I were to make a small company to make, make water bottles, and I have a process where I make the plastic and I have to clean some stuff up and I have some wastewater and I try to get some stuff out of it, but maybe, and I'm not sure, I'm just making the water bottles, maybe there's some plastic chemicals associated with that are in my waste stream. So if I follow the EPA's directions and they tell me if you do this, then I'm fine, great, I can make them, I can just follow those directions, I'm fine. If that was not the case, and I had some chemicals in my water and I'm discharging that water, I then have to study and say, oh, no, I do not have those chemicals, I've removed them, and those chemicals don't harm anybody if they get out in the water. But if somebody out playing in the receiving water then got sick, maybe were injured or something, had some complaint, and they thought that I did it, then the burden's on me for having maybe discharged this. So then I have the burden of proof to say, no, I didn't discharge it, or no, this doesn't cause harm. I don't have, as a small business owner, I don't have the kind of money to do a full-scale research and publish the results just to show that this is not toxic, right? Whether or not it is, or to find that. I don't have the capability to do that up front before even starting my business, right? Which would maybe be the appropriate thing to do if I was concerned I might harm somebody. So if you stop and think about what it takes to justify a discharge of pollution while keeping the public safe, while not harming somebody by doing so, there's actually a lot that goes into that. So it's the regulatory system allows a great opportunity to be able to do so in a protected manner. Okay, so then we have conventional pollutants. These are the first ones that I guess become pretty obvious. We call them conventional. This is usually what primary and secondary treatment really is designed to handle first and foremost. So we have these conventionals and then we have some extras. So the conventionals really are maybe the most obvious. If you discharge water that has a lot of what we call biological oxygen demand, then downstream, the water becomes deprived of oxygen and the fish die, it stinks, everybody's unhappy, right? It's conventionally obvious, I guess. So we'll talk about the these few. First of all, this biological oxygen demand. This is something we'll spend more time on, but this is a measure of the type of substances that can feed microbes, basically. It's kind of like if you were to put sugar in water, bacteria could eat the sugar. That's an oxygen demanding substance because the bacteria are going to eat it, go through respiration, consume oxygen, and emit CO2. Right? They're just going to be going through respiration. So it's the amount of oxygen demanded by microbes for this respiration when they eat organic matter. So this is a loose, it's a way to quantify the organic matter, but in the units of oxygen consumed, right? So that way we can know something about how much oxygen is being used. That way, if we have a wastewater discharge into a stream, we can know whether or not that stream will become oxygen depleted, because we know our fish and wildlife need oxygen in the water, and if we drop it too far, there are problems, right? So this is kind of the scheme of this BOD, biological oxygen demand. Okay. Along with that, so we can kind of conceive of BOD as microbe food, and with that, if we take oxygen plus these dissolved organics, that BOD, what we're going to get is CO2 and more cells, right? So that's the purpose of bubbling air through our waste, like we see here in this activated sludge basin. That's kind of the purpose. We're just going to let the microbes do that before we discharge it to the river or stream, and we'll be happy. Next would be total suspended solids, TSS. So suspended meaning they're floating around in water. Solids meaning they're some sort of particle, typically. We could also have total dissolved solids, which would be something that if you evaporate the water, you have some solid stuff remaining. That's kind of the difference, right? Total suspended solids you pull out with a filter. We generally don't want to discharge a bunch of particulate matter, right? It would make things messy downstream. It could also cause problems ecologically for just coating everything with fine particles, right? It would be a similar problem as if you were to kick up a bunch of mud, with construction or some disrupting the sediment floor in a stream or a river, and then your water kind of looks a little bit like this, and you can tell that that's not a good environment for ecology, right? For aquatic plants that could be covered, no longer able to receive sunlight. For fish, maybe it causes problems for them with their gills. Maybe it covers their eggs that they're laying and kind of disrupts them from being able to reproduce, all sorts of problems, right? So that's, again, kind of an obvious bunch of particulate matter. We don't really want to do that. pH, likewise, if our wastewater had an extreme pH one way or the other, that would be important, so maybe would need to be adjusted. Fecal coliforms, kind of a measure of how much risk we have for spreading disease, right? Pretty obvious. So this would be a disease indicator. Now, what's interesting is not everybody, not every country disinfects their wastewater. Some countries just say, okay, well, it's wastewater, and we're going to discharge it. We're going to treat for a lot of these things, but we're just going to allow nature and the assimilative capacity to take care of that, and there's just going to be some exposure. France, for example, typically doesn't disinfect their wastewater. Okay, last one is oil and grease, and that might sound a little obvious, but it's if you discharge a bunch of oil and grease in some industrial process, well, you're going to get a layer of oil and grease on the surface of your water, and well, that might not look too nice. It might cause some ecological disruptions, but it also could set your lake on fire if you're not careful. So one of the reasons that's in there is that is something that has happened. We've actually seen there were several several cases in the 50s and 60s and maybe into the 70s where there was just unregulated discharges of oil and grease from different industries. And so eventually you get an oil slick, and if you have an ignition source, then you have a big old grease fire. And do you guys know how to put out a grease fire? Okay, so if you got it in a pan, take it away from the heat, put a lid on it. Good stuff. What else? Not water. Right. So not water, and why not?
Because it'll just make it expand. I don't know the chemistry, but I know it makes it worse.
Yeah, it makes it worse. If you have if it's in a pot and you pour the water on, the grease normally floats. So the water is going to sink, and then it's going to boil because it's really hot. And what happens when you boil water? Steam, it expands. What happens if you do that while it's covered? Kind of explodes a little bit, right? And so really quickly, this water that you just poured on it suddenly is sort of exploding, and it's throwing this burning grease everywhere, right? So there's some interesting, I saw recently a video of a firefighter demonstrating. This took it was all suited up and everything. It had a pot, boiling grease, or burning grease. It just takes a little can with a stick, just dumps the water, and it just everywhere, flames, big fireball. So really crazy. So then you think about, well, how do you fight a grease fire that's on a lake? Probably pretty troubling, right? It's going to be hard to suffocate it. It's going to be hard to, maybe throwing water on it is not as bad as in indoor situation because there's maybe more space for it to go, but it's still just kind of not doing anything to it, right? CO2. You could try suffocating it with CO2 or something, but are you going to just do that to the whole city? You almost maybe have to let it burn out, right? It's kind of crazy. So a big problem, and in fact, there's a more recent example I can share with you. This was 2015, a river that had a pipeline that burst. So it's a grease fire. This is in Moscow. Still is a grease fire, but not from a wastewater discharge, but from a burst pipeline. If I have some. So quite impressive. Let's see the sound for the next. Okay. Yeah. So pretty crazy there. I might have to figure out how to get the sound going because I wanted it for something, but we'll come back to that in a minute. Okay, so yeah, oil and grease. Turns out that's important to remove from your wastewater, right? So that's one aspect of wastewater treatment. So there's the article to that. There's also an article here talking about this picture. I think I posted this to Moodle. And it's this article here. So it talks about that same river where you had the fire. You can kind of see this guy's hand coated in grease from dipping it in there. So it's a neat article. We'll come back to a bit of it. It kind of describes some of the conservation efforts and what impact they've had. One of the things that's hard to appreciate over the course of several decades is the actual progress that's been made given regulations like these, right? When's the last time you heard about a river catching on fire, right? Aside from today, probably haven't heard of that, right? Turns out that used to be a big problem. Okay, so then that's the conventional pollutants. We also have toxics. heavy metals, organic compounds that are toxic, carcinogenic, that kind of stuff. We have a list of those in the Permit Writer's Manual I was going to show you, so we'll come back to that. And then we have so-called non-conventionals. That's kind of everything else, right? If we use chlorine for disinfection, chlorine's not something we normally find in our wastewater unless we added it, right? But it could kill organisms, right? That's kind of what we're using it for, is to kill microorganisms. But it would be toxic when we release it, so we need to let it decay or to quench it first. And so it's not toxic in that that sense of like it's a heavy metal. It will always, any amount of it is going to be a problem, but it'll be something that we ought to take care of. Ammonia is pretty similar. It actually turns out that ammonia, it's certainly a naturally occurring thing. We'll generate a fair amount of it along the way as we're processing and digesting waste, but it's toxic at several milligrams per liter quantities, and so we want to make sure that when we discharge it, it's beneath the toxic threshold. We'll have some sort of assimilation capacity to make sure that if the river or stream or whatever is taking on that much ammonia, that it can assimilate that into the natural processes without overwhelming it. Nitrate and nitrite are kind of similar, a little less toxic. Nitrite is kind of in between, is a little bit more toxic than nitrate. But overall, each of these three are nitrogen containing macronutrients, essentially. Nitrogen is, for nutrients, we've got carbon, it's the most important, then nitrogen, and then phosphorus. Those are the three big ones that you could look at. Even fertilizer, right? It's typically nitrogen and phosphorus. Plants don't really need carbon because they're going to take it from the atmosphere, CO2. But for most of life, you have to have some carbon source. That's usually related to the energy too. Like sugar could be carbon and energy. And then you're going to need nitrogen and phosphorus. Those are sort of the basic building blocks for most of life. Okay, so anything else like that that might be a problem, but is not captured in the conventionals and it's not one of these toxics, then that would be here. Okay, so on to primary treatment then. Actually, you know what? Not before that. Let's talk about that Permit Writer's Manual. Then we'll go there. So, in 2015, I had a chance to go to a super exciting workshop. I'm saying that with some sarcasm here. It was a nice workshop. It was about a week-long course. You go into kind of a office building, and this was in Chicago. It's neat to go to Chicago. But basically, it's kind of like 8 hours of lecture a day, but the lecture was sort of like, all right, let's look at this number, and in the Cuyahoga River, here's what happened. Just very monotonous, and you kind of had to try not to fall asleep because it was going to put you to sleep. So it was interesting. Hopefully I can make it a little more interesting. So I just wanted to, I posted this in case you wanted to see kind of the bigger scope. It wasn't that bad. I like to joke about it. So we've already talked a bit about it, so I'm just going to skim through this first section, this first chapter of it for a couple minutes, point out a few highlights. We'll take a look at there's a table of the toxic compounds that we know about. And whatever I forgot to mention, hopefully I can add it in here with you. That's what I plan to do here. So, okay, early on, the first semblance of some sort of wastewater discharge control actually came from navigation. So keeping navigable waters navigable was kind of the first effort towards keeping some control of wastewater. That was the Rivers and Harbors Act. So I don't know, you can't discharge too many, or you can't send too many dead trees down the river or something. It had to do with that. Later that became 1948, the Federal Water Pollution Control Act. That's when we started saying, okay, we have some human health concerns here. This is probably not good for us. Let's start acting on that. 1965 was the Water Quality Act. Okay, maybe we've had one too many lakes on fire. And so that started requiring standards for interstate waters. And a lot of the federal guidance is kind of from an interstate waters type of a situation. Okay, so let's just, from that article, this is the Cuyahoga River in Cleveland, Ohio, August 1st, 1969. I'm just going to read this clip. Some river, chocolate brown, oily, bubbling with subsurface gases, it oozes rather than flows. Anyone that falls into the Cuyahoga River does not drown, Cleveland citizens joke grimly. He decays. The Federal Water Pollution Control Administration dryly notes, the lower Cuyahoga has no visible signs of life, not even low forms such as leeches and sludge worms that usually thrive on wastes. It is also literally a fire hazard. So that was the state of things. That photo is from 1952. This article was 1969. So that fire was early in the 50s, and it was still known as a fire hazard by 1969. So 1970s, when we really started getting some progress towards what we currently have as our current regulations. This was kind of the first draft Refuse Act permit program. It was struck down because it wasn't constitutional. It wasn't. It was perhaps a good direction, but poor implementation sort of situation. Which, by the way, like present day, if you look at how legal things and law stuff, political stuff happens, you'll probably find that actually happens a lot more than you realize. It's easy to see looking backwards, but maybe there was an important issue, people made a big deal out of it, maybe they were, trying to get elected or who knows what from it. Hopefully there's some balancing that happens, and eventually we have something that is actually good and balanced, right? But it may take some time. So, current program, we have the Federal Water Pollution Control Act amendments, 1972. That kind of laid the groundworks for the Clean Water Act in 1977 and the Water Quality Act in 1987. Let's see. So here's where we see that the initial intention for this thing was to eliminate the discharge of pollutants to navigable waters by 1985. Just eliminate them. None of those. None of those pollutant things, right? That was their goal. But maybe if we can't, then at least by 1983, wherever attainable, a level of water quality that provides for the protection and propagation of fish, shellfish, and wildlife, and provides for recreation in and on the water. So that turns out to be the more reasonable aim, right? And we still don't meet that in every single scenario according to how we measure it. Some natural bodies of water don't meet that just by nature, right? Some scenarios just don't support life very well, or whichever aspect. And then it also says prohibit the discharge of toxic pollutants in toxic amounts. That one's a little easier, right? We can identify, hey, that's toxic, let's not discharge that, right? That's a little simpler. When it comes to like temperature, maybe there's some wiggle room there where we could say, all right, if we're considering temperature pollutant, maybe we, instead of eliminating it altogether, we'll get, wherever attainable, a level of water quality that provides for these intended uses. So that's kind of how it morphed. That's the direction it went. Basically, the NPDES program, so it was the EPA, but then they authorized different states. Almost all the states have their own NPDES program now. And the permits actually require some fee. So when I was in Michigan, I learned that the Detroit Water and Sewerage Department, their wastewater discharge, which is absolutely enormous, for them to get a permit, they pay something like $300,000 a year for that permit to discharge the water. It might actually be a lot more than that. But it's a a sizable amount, but it actually pays for this permitting program. So this is one of those scenarios where people want to discharge waste, so they pay for a permit, they pay a fee, and the large discharges require a large permit, and that actually pays for that regulatory system to be in place. Works out reasonably well. Okay, 1976, here's where a bunch of toxic priority pollutants were described. There was 65 categories, 129 pollutants, and then this is also something that would be updated every 5 years, I think. And in addition to that, they identified certain industries that tend to produce certain pollutants. So if you have a textile industry that they're going to be dyeing their clothes to be certain colors, well, chances are good that they're going to have dye molecules as a pollutant. And so if some of those are toxic, they can identify, oh, hey, here's this class of pollutants. We expect these particular molecules to be a problem. Therefore, in some cases, they would say, all right, if you're this type of industry, we'll give you a technology-based effluent limitation. So that means you must use this type of wastewater treatment. Maybe it's activated carbon to do adsorption. We haven't really talked about that much, but that can catch chemical pollutants pretty well. Maybe it's some other kind, but it'll say this technology is sufficient, so you have to use it in this manner in order to discharge this type of waste. And that way kind of simplifying not having to necessarily check for the pollutants all the time, all day, every day. Okay, let's see. Talked a little bit about that. 1987 is when stormwater permitting was added as a way, if, for example, if you have a oil changing business, you do a bunch of oil changes every day, chances are that you're going to have some grease that gets on the ground. If you're not careful, then it rains, all that oil and grease is going to come off the ground that was spilled and get into the water. So there's maybe some basic prevention, have a little oil and grease trap within your drainage and intentional drainage. Maybe that's all it needs, right? It's pretty simple, straightforward. Those types of permits, I did a lot of them. It was kind of like shoveling paperwork along. It was like, okay, make sure the info's up to date. This will be good for them for the next 5 years. They just have to affirm that, yeah, here's our permit. We paid for it. We're good. So some of those can be pretty simple. Actually, there's an interesting scenario right now. If anybody you've been following SpaceX, they're trying to launch the really large rocket, and they have this very big water deluge system now to catch all that energy, protect their launch pad, and that's what they're doing is spraying a whole bunch of water right underneath where the rocket is firing. And they've had a stormwater discharge permit for the facility for whatever runoff might happen. But now there's some question about, do they need more than a stormwater given that they're using this deluge system that's probably hundreds of thousands of gallons in a few seconds. And I'm intrigued to see where that goes, because it's maybe that does constitute a discharge beyond what stormwater entails. But it's also, I know they're frustrated because they've been ready to launch a rocket, waiting on all these regulations and stuff. So that'll be interesting to kind of see how that works. Okay. We talked a bit about what a permit is. It's like a license. Generally, it's referring to point source discharges for the most part, some sort of a pipe or a ditch. One thing that has been an exception, and there's been a few updates on this actually since this document, is agricultural runoff. We're trying to grow food. We have to fertilize it, so we're adding pollutants, nitrogen and phosphorus. And then if it rains or if we're watering the stuff, then we have runoff of polluted water in that sense. That's something that in a way we have to just simply, on some level, we have to be okay with it because we want food, right? On another level, perhaps there are best practices, perhaps there are ways to work with that, but at minimum, we would not generally consider an irrigation ditch itself to be a water of the United States that we need to protect that water's intended uses. So there's some back and forth going on lately about that. Okay. So speaking of waters of the United States, that's typically how we define what do we regulate. It's all interstate waters, all waters that are currently used, were used in the past, or may be susceptible to use in interstate or foreign commerce, including waters subject to ebb and flow of the tide. All other waters that could affect interstate or foreign commerce, all impoundments of water in the United States, tributaries of the above four categories, the territorial sea, wetlands adjacent to waters identified above. Okay, so there's a bit of controversy now, or recently, about the wetlands adjacent to. So originally, this is all coming from kind of the navigation stuff. So you see it kind of tying back into there. And there are some issues where the wetlands adjacent to the waters, it is important ecologically to protect wetlands in general. And the wetlands do have impacts on the ecology of a river or some other larger body of water. It's actually not like a discrete, here's the shore, here's the water, and here's the wetland typically, right? That's actually much more merged. And so there's good reason to try to protect the wetlands, prevent discharge of significant waste. But at the same time, there's definitely room for arbitrary judgments and penalizing people for who knows what reason, because you could maybe make a case that that's a wetland, and so therefore you have to act differently. So that I'm aware that there's some issues there. If you're discharging enough water, you might end up turning the wetlands into a stream. So at some point you might just run into that also. So I think that the fact that we have to protect that level of discharge anyway might make that a little bit of a, like the protection of the wetlands themselves under the NPDES program might not actually matter too much. I don't know. There's certainly some cases that have issues there. Okay, some history on Supreme Court rulings. I think there's been some more recent ones. So I should add that as slides actually. All right, groundwater is a different system. You can sometimes discharge to the ground, pump water down into the ground like we pump water out sometimes. That has its own permitting program. It's not quite as common. I'm not as familiar with it, but it kind of follows the same overall shape or approach to our surface discharges, right? We want to protect whatever we might want to use the groundwater for. We have to make sure that it's not going to go and contaminate our drinking water aquifers and things like that. Okay, so an article June 20th, 2009 about the Cuyahoga River revisited. So some progress since 1969 and all those regulations here. The first time Gene Roberts fell into the Cuyahoga River in 1963, he worried he might die. Mr. Roberts smelled so bad, his friends ran to stay upwind of him. Recently, he returned to the river carrying his fly fishing rod, and in 20 minutes, he caught 6 smallmouth bass. It's a miracle, he said. The river has come back to life. Today, the Cuyahoga is home to more than 60 species of fish, said Jim White, executive director of the Cuyahoga River, blah, blah, blah. Beavers, blue herons, and bald eagles nest along the river's banks. Smallmouth bass, by the way, are pretty particular about having good quality water. They like a fair amount of oxygen. They don't really like hanging out down here in Louisiana because it's generally warm and less oxygen around in the water bodies. So unless maybe there's some in some of the rivers, you generally won't find them too often. And the reason he would have smelled so bad is because it would have gone anoxic, right? It would be oxygen deprived. The oil and grease on the top would probably also prevent oxygen transfer with the air, so it would have just kind of smelled like rotten eggs if you were to break the surface. It would be pretty nasty. I expect. So that's probably kind of what was going on there. All right. So there are some assessments of how many bodies of water are considered impaired or for intended uses. There's a lot that goes on there. There's a lot of ways to measure. You can do rivers. You can do lakes. You can look at how they're impaired, why they're impaired, and stuff like that. Here's the list of priority pollutants. So you'll see things like benzene, carbon tetrachloride, chlorobenzene, all sorts of known toxic pollutants here, all classified here. We see we're up to 129. These are also going to include toxic heavy metals, lead, mercury, nickel, selenium, etc. So this list is kind of the that toxics and heavy metals, or the toxics table. If we find more, they'll be added, right, in terms of like common industrial pollutants. Okay, I think that's all I wanted to show you from this. If you are interested, this whole set of slides is on our Moodle. Okay, so I wanted to talk briefly about primary treatment. So primary treatment is that first sedimentation, but also the grit removal, screen, basically kind of management of your wastewater collection system, which would include your sewer system. And the first thing I want to say is, if you ever see flushable wipes, they're not actually flushables. Don't flush them. Okay. And I have a little video on that, so I need to see if I can get the sound to play, because it's entertaining to highlight that point. So let me see for a moment if I can get the sound to work. Oh, we heard that? Okay, great. All right, let's do it then. Okay. So, about flushable wipes. Well, I thought the sound was working. Ah, that would be why. Come on. There we go.
So-called flushable wipes getting stuck in the sewer systems.
I have never seen one dissolve.
They have to remove them on a daily basis.
Look at that. Okay, so that's why we have grit removal and screens and bar racks and stuff, because yeah, that's pretty nasty, right? And that's also, you know, that probably doesn't make it to the wastewater treatment plant. That just sits there, and somebody's eventually going to have to clean that out. So fortunately, there's some high-paying jobs out there, right? Because no one else wants to do it. All right, so that's what I have to say about flushable wipes. Don't. I always kind of laughed that, you know, the guy's like, I never seen one dissolve, and I for a while I was like, well, would you see it if it dissolved? But I guess maybe you could see like you might see half of it dissolve if it was hanging out of the water or something. I don't know. Okay. I think the claim for flushable wipes is that they're going to make it through your plumbing, and so then you don't have to think about it. Like, it'll flush, I promise. Maybe it flushes, but does that mean you should? Our toilet paper is designed so it does dissolve, right? And you know that if you accidentally get it wet when you didn't want to, right? It starts, you can tell it's not going to last very long. Yeah. So it's got to go somewhere. All right, so this next video, this is kind of like an advertisement for this company's stuff. I find that advertisements for like water treatment technologies kind of are informative. So I'm not here to advertise for them necessarily, just kind of showing you an example of a bar screen rack kind of thing. So they basically have this system where water's flowing through. You'll be collecting these non-flushable wipes, etc. And then it has kind of an automated system to scrape it, just to do kind of a continuous operation that can remove this trash debris kind of stuff over time. And does a decent job automating it. I mentioned already visiting the Detroit water treatment plant. They had a room full of things that looked a lot like these. It was a pretty nasty room, and there was kind of garbage and junk everywhere. You know, all of those items that they mentioned not to flush, you could see them around. It's pretty dirty business, but at least there's a fair bit of automation involved, right? So each one of these would have like a dumpster right next to it so that it would dump into them, and you know, just you know, some are perhaps more advanced than others, but ultimately you're finding some way to collect the stuff and eventually, yeah, just dump it in a dumpster or something, right? So that's, you know, I'm sure you can get high tech with them, and maybe this is kind of high tech, but it's sort of a low tech problem, right? There's stuff in the water that you don't really want to go through into the other plumbing and all the other stuff that, you know, you don't want it to get past this spot, so you have some sort of a screen bar rack type of situation. Grit chambers are kind of similar. They're usually, a grit chamber would maybe look like a barrel that has a bunch of small holes in it, so it could catch little pebbles kind of thing, but water could flow through this barrel, and it would just like maybe be turning or something and getting the pebbles removed from the water, and the water just goes through. I've seen some grit chambers like that. Basically, this is all protective of the rest of the plumbing in the system. and the wastewater treatment. Okay, and we talked about that, and so I think that's all I've got for you today. Any questions? All right, we'll see you on Thursday.